Hi everybody, welcome back to Quantum Field Theory, a Student's Perspective. I want to continue today with a canonical quantization, and so we're going to do lesson 3, canonical quantization of scalar fields. 3B. And the references are the same as before. Like I said, every book does it a little bit differently. Orkin and Drell, chapters 11 and 12, and Hatfield, sections 3.3, Ryder, section 4.1, Coleman, where much of this material is taken from, is section 4.4, Czernecki, our main course textbook, is chapter 3, and Peskin and Schroeder, chapter 2. Okay, so we've done canonical quantization from a bottom-up approach. Let's call it the bottom-up Fock space approach. And then last lecture we worked on the top-down, let's call this like a physical approach. Top-down canonical approach. Sort of like a turn the crank without thinking. And we, last video, we reviewed this approach at lightning speed for classical particle mechanics. For quantum mechanics and classical field theory. And today we're going to fill in the missing box. You might remember from the last lecture. And do canonical of quantum field theory in the context now. Some of the stuff is going to seem like we're repeating stuff that we did earlier, and some of the stuff that we did earlier I'm not going to repeat. A lot of this is like a chicken and egg sort of thing. Before we went forwards, now we're sort of going backwards. But the general idea I think is clear, and I'll try and do this lecture as if it was just a traditional 1960s canonical quantization approach like Borkin and Drell do it. So we start with the Klein-Gordon equation. which is a scalar. I'm going to do a real scalar here. A real scalar Lorentz invariant field. So the Klein-Gordon equation is just, and I'm going to work in the Borkin and Drought metric in this lecture. So the time component is positive in Minkowski space. Or the second. Okay. Now, we already have the Lagrangian for this field, and that's what we need, but I'm just going to work backwards. Pretend we don't know the Lagrangian. And you can do this for a lot of theories. It's just going backwards. So we define del phi of x, our variation in the fields, phi prime of x minus phi of x. This is an infinitesimal variation. Multiply this by the field equation and integrate over space-time. So we get, whenever we do this, we always have finite integrations for time, but we integrate over all space. Some people just neglect to even say that, but it's not really that important. Now, as usual, the variations vanish at the endpoints of time. And we're also going to assume localization so that all fields, derivatives, etc., go to 0 as the absolute value of space goes to infinity, plus or minus infinity. So with that, we can always integrate. We don't have to worry about boundary terms now. We can always integrate by parts. We'll either have a spatial thing, in which case we use the localization thing, or we'll have a time thing, in which case we use our usual Lagrangian formulation that the variations vanish at the endpoints of time. And if you work this backwards, for instance, you can get let's see, del phi, the second partial of phi with respect to T2 is equal to minus 1/2 partial of del phi with respect to t times the partial of phi with respect to t plus the partial of phi with respect to t partial of del phi with respect to t. And you can see this just by imagining you integrate this by parts. The integral of u dv, and we get a minus sign which cancels this minus sign, and we'll get del phi times the second partial phi with respect to t. Each of these terms is the same. So when we do that, we're going to end up with just, again, doing everything in reverse from what we usually do. I don't want to work it out anymore. My signs may look like they're off, but they're really not, I don't think. This whole thing is equal to 0. And so if you remember our basic Lagrangian thing, our Lagrangian is we have this del, the integral of t1 to t2, d4x. Here I'm not going to have L of phi, comma the partial of phi with respect to x mu is equal to 0. So look, we bring this del over here all the way out there, and so we end up getting our usual Lagrangian for the Klein coordinate equation, which, like I said, you can derive this, just by looking at it. Okay, and this is the same as before. So if you ever have an equation and you're trying to figure out what the Lagrangian is and you can't find your book or something like that, just multiply it by a variation and integrate and use some integration by parts. Okay, now from this Lagrangian, using our usual turn-to-crank approach, I'm going to leave out the vectors a lot of time, but technically, an x without a vector has 4 components. So this is our canonical coordinate, and then our canonical momentum is given by our usual approach, pi. Again, I'm going to define that as pi of x, the partial of the Lagrangian with respect to phi dot x, and this is just equal to phi dot x. So everything's very simple with the scalar field. And now to make it quantum, we have the equal time canonical commutation relations. Now, the theory we're doing today, we're never going to have any problems because it's very simple. It's a scalar field theory. If you had tried to do this for electromagnetism, you'd run into difficulties right away. There are ways to canonically quantize the electromagnetic field, but we have to change some things. I won't have to change anything here, but just be aware that not everything we're doing here is going to work all the time. Anyway, our canonical quantizations are simply equal time. That's the key thing here. So the phis commute with each other, the pi's commute with each other, and the usual one that we get in quantum mechanics, the coordinate This is the important one. Okay. Big box around canonical quantization relations. Okay. Then we, we do the same procedure to derive the Hamiltonian. We get a Hamiltonian density. And the Hamiltonian density is defined in our usual way. Nothing changes here. And for the theory we have, it's going to be pi squared, since phi dot is equal to pi. If I go back up here, so all you have to remember is pi is equal to phi dot. So I have pi squared minus 1/2 pi squared minus del phi squared minus m squared phi squared. And so our Hamiltonian density ends up being 1/2 pi squared plus del phi squared plus m squared phi squared. And it's important to notice that this is great. It's great because every term is positive definite. So our energy density is bounded from below, and we're not going to have any problems with that. So now I'm going to do something we did last time in the classical context. I'm going to show that the standard Heisenberg equations for operators in the Heisenberg picture, they're the same. I could put them either way as the Hamiltonian. It's Hamilton's equations. I showed this in the classical context, and it should be obvious that it's going to work in the quantum context, because the whole idea of the quantum thing is to replace, is to use commutators with del functions, which ends up working the same thing as derivatives. But I'll show it anyway. So, oops, sorry. So yeah. This is the Heisenberg equation of motion for any variable, any operator that's not doesn't have explicit time dependence. It's the commutator of the Hamiltonian with the variable. So here you just plug in now. Since we're taking the commutator with phi, the only thing we have to worry about is pi's, because phi's commute with phi's. So I get pi squared y this should be a y comma t. Okay, and now using the usual Leibniz rules for commutators, I'm going to take a pi out here and have a commutator of pi of y with phi of x. Then I'm going to put it on the other side, but since we end up getting delta functions, it doesn't matter. So this ends up being the integral of d3y. There's an I that will come from the delta function, which will give me a minus sign, but we're taking the commutators in reverse order, so we get another minus sign. So we're going to get the integral of d3y pi of y comma t del 3 x minus y, and this is just equal to pi of x comma t. So that's our definition that we had earlier. As I said the only thing we have to remember here is that pi of x comma t is phi dot. So one equation for the derivative of the phi gives us the definition we had before. The second equation is a little bit more interesting. So we do pi dot and as before we turn the crank. Now here what we have is we have two terms here, two phi terms, which don't compute with phi, so we're going to end up getting two terms here. So I'm going to have 1/2 del phi squared with the pi, and I'm going to get another term, 1/2 phi squared y comma t comma pi of x comma t. Now the second term is routine. Sometimes students are bothered with this term here. They don't know how to handle this gradient. Well, it's not really hard. The best thing to do is to integrate by parts. Well, actually, you don't. This is a del phi dot a del phi. So let's just write this term. The integral of d3y 1/2. Use the usual Leibniz rule. So it's going to be del phi. I'll leave out. Oh, I won't leave it out. Dot commutator del phi y comma t comma pi x comma t, and then the other term is going to be the same thing. I'll write it out. Okay. Now, still a little confused. I know people are still a little confused by this, but we can just take the gradient out of here. So it really becomes the integral of d3y 1/2 del phi dot del. And the del, you should think of this is a del y, obviously. Del y I'll put on here times the commutator of phi of y comma t comma pi x comma t. And the other term is basically the same. Now I can evaluate this because I've taken the gradient out of here. So I get or even better, Now just do an integration by parts. You know, the integral u dv. Just do an integration by parts, and I get a minus I, the integral of d3y, 1/2. I'm going to have del squared phi of y comma t commutator plus the other term, which is the same. And now I get minus I, the integral d3y. I'm going to combine both these terms with the same. Del squared phi of y comma t. Now I get I del 3 x minus y. And the integral is, the i's cancel, the integral is trivial to compute, so we just get del squared phi of x comma t. Then we have to add the term that I didn't bother to evaluate here. This is going to be, I left the m squared out of there. Okay, this should be a m squared. Okay. So now I'm going to get the total thing. I'm going to get pi dot x comma t is equal to del squared phi of x comma t minus m squared phi of x comma t. And let me just, doesn't seem like I got that sign right. Oh, because I'm going to be multiplying. I have an I out in front, and I'm going to get an I in here, so that's right. Okay, and now this, remember, pi is phi dot, so this is just phi double dot x comma t is equal to del squared phi x comma t minus m squared phi x comma t. So this is the kg equation again. Everything is consistent. Okay, and we are happy. I'm sure the first time people did this, they weren't 100% sure that it was all going to work out. And so they were probably pretty happy. Okay, now let's just go back to exploring the quantum field theory again. The kg equation is linear. So we can solve it. We can solve by Fourier integrals. So we're just doing an expansion here. So we write phi of x comma t. Now, for this lecture, when I use like A, and everything I'm using is the non-relativistic normalization. So it will differ a little bit from like Shineki, but it's consistent with other books. Like I said, there's two main ways to do it. And you either go AA dagger equal 1, or you go like AA dagger equal 2 pi cubed 2 omega k del 3. So, just in case you're wondering. So I'm just going to write d3k 2 pi cubed 2 omega k The 1/2 is the key here. That's what makes this non-relativistic normalization. And we're going to write it as 8p e to the minus I omega pt plus I p dot x plus a dagger p e to the I omega pt minus I p dot x. And you can easily see if you substitute this in the Klein-Gordon equation, by definition, as usual, omega k here is plus square root of k squared plus m squared. And you can just take the derivatives and substitute it in there, and you see that we solve the equation. The a's here are just operators. And as we'll show, they're independent of time. So just for some convenience, I'm going to define fkx as being 1 over the square root of 2 pi cubed 2 omega k e to the minus I k dot x. Okay. And then there's another notation that's commonly used in quantum field theory books. If you have like something like AT, this is called like a backwards and forwards derivative. It can also be with mu. We're going to only use it for time here, but it can also apply with space as well. And this is just defined as AT, the partial of b with respect to t, minus the partial of a with respect to t, b of t. Notice we don't change the order here. So you can easily establish I think I do it in the notes that I'll provide along with this, but I'm not going to do it here. You can easily establish that fk star x comma t fk prime x comma t d3x is equal to del 3k minus k prime. This is the like orthogonality relation that you're going to have to establish some results. I left one thing out here. The key thing here is that phi is real. So I could use a dagger. If you take the complex conjugate of this, you see this goes into this. So in order for this to be unchanged, AP has to go to AP dagger, and AP dagger goes to AP. Sudnecki discusses this a little bit more detail, showing why that has to be exactly the case. If we were doing a complex scalar field, which I may do in a few videos, that would not be necessarily the case. And then you can also show that the integral of so using our definition for phi, it's very easy to show. It's very easy to do the inversion. I'll do part of it here, but it's very easy to show that fk star and check one thing. I think I might have left off the omega k there in my notes. No, it's right. Okay. So using this, it becomes very easy. It's just two linear equations. And by the way, if it's easy to see what's going to happen here when you just substitute in phi, and when you substitute in phi dot, it's very easy to see what's going to happen. So when you solve this, you're going to end up getting AK is equal to I, the integral. So this is just inverting. Some books just show it to you. I put in a step or two here, but I'm not gonna show it all. These back and forths are with the minus signs are actually difficult to do in your head. I've found out over the years. So that's AK. And it's pretty easy to show that this is independent of time, because each of these is a solution of the, this is like by Green's theorem, and each of these sort of solves the Klein-Gordon equation. So it's not too hard to show that if you take a time derivative here, this will vanish. Okay. And obviously A dagger K is the same thing. Minus I. We don't need the phi star because phi is real. Okay. Now, and all the books do this, Signecki does it, everybody does it in a certain way. We can compute what we want to compute. See, when we did the bottom-up approach, we sort of started with knowing what this was. Here, we're going to just compute it. I'm just going to write it down. I'm not going to do the whole computation, but we have like our AK. So this is going to end up being and we can do this at equal times. We can take our fields at equal times because any time for these will matter. They're all the same. Okay. So do a little crunching. Do it on a piece of paper. We'll get our usual commutation relations for the creation operators. And similarly, we'll find, AK prime is equal to A dagger K prime equals 0. So now we've sort of come full circle. We've gotten back our creation and annihilation operators, and they're easy to interpret and everything. Now, if you do a detailed calculation, which Signecki does, and I really encourage you to go so you do a detailed calculation. And you're going to end up getting that h is equal to 1/2 the integral of d3p a dagger p AP. These should have vectors on them, but you know that what they are. Plus AP a dagger P. And there should be an omega P here. So this is our Hamiltonian, and if you use the commutation relations, you'll end up getting this is where we started when we had just our relativistic formula, and we said, why couldn't we just continue with this? The answer is we wouldn't know if we had Lorentz covariance. We wouldn't know if we had fields that commute outside the light cone and everything. So doing it the canonical approach, we sort of establish all that on the way. This, by the way, is our usual vacuum energy. And we define normal ordering. I'm not sure if Sudnicki covers this or not right away. Eventually he will. Normal ordering just basically says if you have a string of operators, I'll just do it for 2 here. You always put the annihilation operator on the right and the creation operators on the left. So in this case, so that's really all it is. Annihilation. Just a way of crossing this out. And because once you get that, you're always going to get things like 0, a dagger, a, 0, which is equal to 0 because a annihilates the vacuum. So, at the end of this right now, and I just want to mention, what's the advantage of this canonical approach? There are other approaches. There's a Feynman path integral. There's there's the Fock space ground up approach that we did earlier. The answer is very easy, and this also applies to the Feynman path integral. Very easy to add interactions. So far we've only treated a free theory. But if we want, we can just go L goes to L minus lambda phi to the 4th. This is going to still be Lorentz invariant. And it's easier to show that we'll still have all those other properties that we want of commutators vanishing outside the light cone. The problem with the bottom-up approach that will fail, and we can do perturbation theory. Because we need the solutions to build up our Fock space. In other words, we need the spectrum. And we don't have the spectrum because our equations are nonlinear. So that ends this lecture. The next few videos I'll have some examples. Not much more to do with canonical quantization, but I'll do some examples. And there's still a lot more to do on scalar fields, as we'll see in the coming videos. We've got things like Noether's theorem and symmetries, and I might have a couple extra videos on non-abelian gauge symmetries just to show you how it works. So I'll see you next time, and thank you very much for watching Quantum Field Theory, A Student's Perspective.